Hello, hello. Total Development Lab back again with another video. And today we will be going over the Affine Cipher. Now, this video is 1 out of 2, and the reason for this video is just for a general overview of the cipher. This is really only for educational purposes. Please don't use this cipher in any real world application. Now, so a little bit about the cipher. The Affine cipher is a classical substitution cipher. It encrypts each letter using a mathematical equation instead of simply shifting letters. Every plain text letter in this cipher maps to exactly one ciphertext letter, and it combines multiplication and addition under modulo 26 arithmetic. And it is considered an improvement over the Caesar cipher, but it is not secure by today's standards. So where was it used? It's primarily an educational cipher, and I mentioned this earlier in the video. It's used to demonstrate modular arithmetic in cryptography, and it's commonly taught in computer science, cybersecurity, mathematics, cryptography courses, but it is rarely used in real-world communication, primarily due to its vulnerability to frequency analysis. So how does it work? All right. Every letter of the alphabet is converted into a number, right? So think A equals 0, B equals 1, Z, all the way to Z equaling 25, right? And then each value is then encrypted using this formula, where A times X plus B mod 26 is the encrypted value of the character that you're on. As you can see here, where it says A is a plain text letter, or X is a plain text letter, A is the multiplication key, and B is a shift key. Now, let's go over an example, right? So in this example, we have the keys A equal to 5 and B equal to 8. And our original text that we want encrypted is simply hello. So what should we do? We start off by converting the numbers of our plain text to the numeral representation of it. So H would be 7, E would be 4, L would be 11, again repeated, and then O would be 14. Then we take our A value, plug it into the A position here. Then we take our B value and plug it into the B position here. And then we have our X now, right? So we go through this entirely character by character. We take the value of H here, which is 7, and then we plug it into X. And that should give us, let's say 5 times 7, which is 35, plus 8, which is 43. And then we mod 26. And that gives us the numerical representation of R, right? Perfect. And we do the same thing for every single character here. So E, we just plug in E here, or we plug in 4 here. So it'll look something like this. So it would be 5 times 4 plus 8 mod 26. And that simplifies to 20 plus 8 mod 26, which simplifies to 28 mod 26. And that simplifies to something like 2 or something. And then, as we noted above, 0 or A is 0 from our character list, B is 1, C is 2. So we say C is the encrypted value for E. Perfect. And then we do the same thing for L, and we do the same thing for O, and then we inevitably end up with this encrypted value from our plaintext string. And this encrypted value is safe to pass to our enemy. They could read it, but they don't understand what it means because they do not have the keys. Now, in order to decrypt it, we need to reverse the cipher by using the modular inverse of A, and that's represented like this. This essentially allows us to recover the original plain text exactly as originally written. So, strengths of this cipher. It's very simple to understand. As you can see, we didn't spend much time on that encryption. And it's more secure than the Caesar cipher, but as we know, it's very insecure, but still works. And it also introduces modular arithmetic. And it's a great stepping stone toward modern cryptography. Now, some weaknesses. Right? The weaknesses here is that it's a small key space. And it's monoalphabetic substitution, meaning that it's with modern day computing, it wouldn't take that long to brute force, right? Especially with frequency analysis. And again, it's really not suitable for modern encryption. But the modern relevance here, right? So although the Affine cipher is no longer used to protect information, it introduces mathematical ideas that appear throughout modern cryptography. And the concepts learned here include modular arithmetic, multiplicative inverses, there's number theory, there's also mathematical transformations. These concepts later become the foundation for algorithms, such as the RSA algorithm, the Diffie-Hellman algorithm, the elliptic curve cryptography. So next video, or part 2 of this series, will implement the complete Affine cipher from scratch in Rust. So we'll include the encryption, we'll include the decryption, and we'll include the modular inverse calculation. We'll also include user input, and then have a complete command line application by the end of the video. So without further ado, thank you for watching, and we'll see you in the next one. Till then, take care.